Okay, for data points x1 hat, y1 hat, x2 hat, y2 hat, and so forth, we obtain the prediction that if y equals ax plus b, where a and b can be varied, the slope and the y-intercept can be varied in such a way as to minimize the total of the squared distances. Our predictions are y1 equals ax1 plus b, y2 equals ax2 plus b, and so forth. Our picture is we have a data point x1, y1 hat, a predicted point x1, y1 equals x1, and y1 equal ax1 plus b, and a vertical distance corresponding to this expression. If we add up all the vertical distances of all the points, we get a series of expressions that look like this. There might be more than 4 points. Here we're just considering 4. And the task becomes to minimize the expression y1 hat minus ax1 minus b squared, and so forth, the same expression we obtained down here. Now I've just written out the first 2 terms in this expansion, and then I have some dotted lines. It's clear that we could go on to any number of data points using the same formula. We could have y3, x3, y4, x4, up to y10,000, x10,000 if we have that many data points. The thing that we have control over, the thing that varies with this model, is the exact location and slope. The things that vary are the exact location and slope of this line, indicated by the slope and the y-intercept. These are flexible, meaning that as a and b change, this total distance is going to change. So we can say that a and b are variables, are y sub I hat and x sub I hat, x sub I, are just numbers. And they're known numbers. So if we want to take a derivative of this expression with respect to a or with respect to b, that's actually fairly easy to do. Each term has the same form, so if we just figure out the derivative of this term with respect to a and with respect to b, we're going to be able to imitate the form of that derivative for all the other terms. Well, let's look at the derivative with respect to a of the term y1 hat minus ax1 minus b quantity squared. What is that? Now, we're not used to taking a derivative with respect to a. We usually have an x or a y or a t or a u or a v or something. But there's no reason a can't be treated as a variable, and we can't take a derivative with respect to the value of a. This expression is a composite expression depending on a. It's the square of a function of a. So its derivative is, first of all, the derivative with respect to a of y1 hat minus ax1 minus b. That's the derivative of our inner function multiplied by 2 times y1 hat minus ax1 minus b. The derivative of the squaring function being 2 times the function. Now, the derivative with respect to a of this is nothing but negative x1. That's multiplied by 2y1 hat minus ax1 minus b. So that's just negative 2x1 times I got an unfortunate location I put my parenthesis here in a bad place. The parenthesis should have been here, so I'm going to fix that. Okay, by the magic of modern technology, I've corrected this expression, and we see that then this is going to be negative 2x1 times y1 hat minus ax1 minus b, which is finally then going to, we're going to multiply this through, and we get 2a x1 squared, and then we're going to have plus, maybe should have made that minus. Let's go ahead and make it minus. Two x1 y1 hat minus 2x1 plus 2x1 b. Now we're going to have a similar term from every one of these squares, so that when we take the derivative with respect to a of the entire expression, we get something that looks like this. First of all, our first term is going to be 2a x1 squared minus 2x1 y1 hat plus 2x1b, and that'll be our derivative of the first term. So our derivative, and I haven't labeled this thing, and I'm not going to label it just yet. Okay, then we're going to have what? Plus 2a x2 squared minus 2x2 y2 hat plus 2x2b plus 2a, this is getting a little tedious now, just replacing the subscripts with 3 and so forth. Now, it's clear that we can do some factoring here. We can say that then this is 2a times x1 squared plus x2 squared plus x3 squared and so forth. And I've done some factoring out here. I'm going to kind of I was going to combine these together, and I've chosen not to do that. That wasn't a good idea. So I then have minus 2 times x1 y1 hat plus x2 y2 hat plus and so forth. And it's clear what this term is going to be. And then I have plus 2b. The b can factor out of all these terms. And I just have x1 plus x2 plus and so forth. Now remembering that this expression here, and it continues to whatever number of data points we have, this expression represents the total squared deviation, or the total squared distance between our line and our data points. So I'm going to call that the total squared distance, and what I've got here then I'm going to label as the derivative with respect to a of the total squared distance, or squared, call it deviation. That's this. Now, one condition for a maximum or a minimum is that the derivative with respect to each of the variables has to be 0. This total squared deviation is regarded as a function, remember, of a and b. We haven't yet taken its derivative with respect to b, although that's going to be fairly straightforward. But we know that a condition for minimizing this, one condition is that this be equal to 0. So that this is equal to 0 for the minimum of the expression that we're trying to minimize. So one condition for minimizing the total squared distance is that this three-part expression here involving the sum of the squares of our x values, our observed x values, the sum of our actual x values, and the sum of our xy products, that this expression be equal to 0. Now let's consider the derivative with respect to b. This is going to be a somewhat simpler expression, the derivative of this expression with respect to b.